Hello everyone. The objective of this video is to go over a couple of problems that cover the areas of 3D vectors, unit vectors, and the dot product of two vectors. So the emphasis will mostly be on the problem solving approach rather than the actual solution, because these are certain type of problems where approaching in a certain way can get you to the answer real fast. So the first one that we're going to solve is the problem 113, which is the same problem that we did in the class. This is problem 113 from the textbook. The problem essentially consists of a stepped pipe, that the pipe goes from point A to point E and then takes different turns along the way. There is a rope connecting point E to point B, which is imparting some sort of a force on the point E. And the magnitude of this force is about 600 newtons. So the problem asks us to find the component of the force F, which is the 600 newtons, along the line DE, which is this pipe around here, and perpendicular to DE. So any line perpendicular. So it's really difficult to show this on the 3-dimension or on the 2D plane. Basically, showing 3D plots on the 2D plane is really difficult. But essentially, what they've asked for are two components of the force F in the direction of DE and the direction perpendicular to DE. So essentially, what that means is think about the force 600 newtons lying on this plane. What they're asking for is if the line DE is if the line DE is somewhere here, we want to find the component of that force F along DE and the component of that force perpendicular to DE. So essentially, this is converting the 3D problem into the 2D problem, where you have a horizontal component and a vertical component for a force. So essentially, this is resolving a force into its two components. Whenever you get such a problem, the first thing to think about are unit vectors. The unit vectors are the real key to solving these problems. Essentially, as I've said multiple times in the class, it's really difficult to visualize a 3D problem. So the best way to approach a problem would be to use or to trust the math. And to get this problem into mathematical notations, what we have to find are unit vectors. Now remember, unit vectors are nothing but some vector that has a magnitude of 1 unit, right? So it's normally denoted by the letter U with a hat. And let's say if you're talking about the unit vector along the direction AB, you're essentially, what you're finding is the position vector AE or AB divided by the magnitude of that same vector. So the magnitude of the numerator. So that would give you the unit vector in the direction of AB. And once you have the unit vector, essentially everything is pretty straightforward, right? Whatever vector you have, whatever physical quantity you have, multiply it, or the magnitude of that quantity multiplied by the unit vector, essentially gives you the physical quantity in the Cartesian vector format, right? So this was just an example. Unit vector AB was just an example here. What we really want here first are the unit vectors EB, along which the force is directed, and the unit vector DE, along which we have to find the components of that force. So whenever you get these kinds of problems, the first thing I would do is to find the coordinates, the 3-dimensional coordinates of each of the points involved in the problem, or in the points that are of interest, basically. So the points that are of our interest here are points B, E, and D, right? So let's start with B. So the 3-dimensional coordinates for B are 0, 2, 0. Just visualize, or just think about, or just look at the figure and figure out how I got into, or how I derived these coordinates. So moving on to E, the three-dimensional coordinates, or the x, y, z coordinates for E are 4, 5, -2. And for D, what I have is 4, 2, -2. So I think we have all the coordinates that is essential to solve this problem. So first, what we have to do is denote f as a Cartesian vector. So to do that, what we would do is so to get f as a vector, we just multiply the magnitude of f, which is 600 newtons, by the unit vector along the direction where f is directed. So that's EB. So you're free to choose either EB or BE, and the unit vector would just be the opposite of one another. However, I'm just choosing EB because that's the direction that the arrow is shown. So to find UEB, or U hat EB, we have the position vector REB divided by the magnitude of REB. And I'm just going to erase this. And the magnitude, or REB, essentially is the coordinate, or the second coordinate minus the first coordinate times the unit vector in that direction, right? So if you take the x, we subtract the second coordinate, which is b, minus the first coordinate, which is, or for e, which is 4. So 0 minus 4 would be -4 I, plus 2 minus 5, which is -3 j, plus 0 minus -2, which is +2 k. So that is the position vector REB. To find the unit vector UEB, we just divide the position vector REB by its magnitude, which is nothing but 4 squared plus 3 squared plus 2 squared. And what we end up with is UEB is equal to -0.743 I minus 0.557 J plus 0.371 K. Remember, these essentially are the direction cosines of the direction EB. And once we have that, we can straight away find the Cartesian vector F, or the force F, which is nothing but 600 newtons multiplied by UEB, which, if you carry out the math, would turn out to be 445.67 I minus 334.25 J plus 222.83 K newtons. Don't forget the units. So now, remember that the problem is to find the components of the force along the line DE, right? So obviously the next candidate unit vector would be the unit vector along the line DE, which is equal to RDE divided by the magnitude of RDE. So RDE can be found out from the XYZ coordinates of D and E. So the coordinates of E minus coordinates of D times whatever unit vectors, or whatever orthogonal unit vectors, IJK, you want to use, right? So to find the x component of the unit vector, we just subtract 4, positive 4, that's x of D, from the 4 of E, right? So that's 0. So 0 I And similarly, the y component would be 5 minus 2. That's plus 3j. And the z component would be minus 2 minus minus 2, which is again 0k. And that divided by the magnitude would just be the square root of 3 squared, which means the unit vector is j. So the unit vector along the line DE is nothing but the unit vector j, which is nothing but the unit vector in the direction of y-axis, which is kind of obvious, right? The DE is parallel to the y-axis, which means they would have the same unit vectors. So once you have that, to find the component of the force F in the direction of DE, we just use the dot product. Remember, the dot product of two vectors is, so A dot B is magnitude of A times magnitude of B times cosine theta. Theta is the angle between the two lines, two vectors. So remember, we're trying to find the x component of, or the component of the force F in this direction. Which means if this angle is theta, to find that component, we'd only have to find the magnitude of F times cosine theta. So to find the component, so coming back to the dot product equation, if you had to find the component of A in the direction of B, we would just do A dot unit vector along B. Because remember, we have to have A dot B is the magnitude of A times the magnitude of B times cosine theta. So to get A cosine theta, we'd have to have the magnitude of B as 1. So that's why we're using the unit vector along the direction of B. So, just want to erase that. To find the component of F along DE, we will just dot product force F with the unit vector of DE. And when you do that, the dot product essentially is just multiplying the components, right? You multiply the x component, negative 445.67, by the x component of the unit vector, which is 0. So that turns out to be 0. The z component also turns out to be 0 because the unit vector's z component is 0. So the only remaining component here is the y component. So essentially f dot u dE would just be negative 334.25 times 1. And that's rounded off to negative 334 newtons. So think about this. We got a negative value here because we took the direction DE for the unit vector. If we were to use the other direction, which is ED, we would have gotten positive 334 as the component. So that's an important distinction that you have to make. So now you have the x component, right, which is this red component that we drew here. Now what the problem asks for is also a component of f that is perpendicular to the line DE, which means it will look something like that. So the component of f that's perpendicular to the line DE. So this essentially would be f sine theta, right? That's what we learned in the two-dimensional problems. But we can calculate that only if we knew the angle theta, right? Which we did not cover here. We did not calculate the angle theta when we got to the parallel component. So another way essentially is the following. So think about these two as not as components but as vectors. So there's a vector in the y direction, or in the perpendicular direction. Let me call it f perpendicular. And then there's a vector in the parallel direction. So this is f dE in the vector notation. So this is no more the magnitude of the component, this is the Cartesian vector notation for dE. And in between them is the force F. So if these three are vectors, we could do vector addition, right? So we can transfer this blue component over here, still remaining the same, right? So if that's the case, we have now a triangle, and we can apply the triangle of addition of vectors. And that would tell us that the vector F perpendicular plus F dE is equal to the vector F. That's the triangle law, right? So we know that, and we know that, right? So, which means F minus F dE will give you the vector F perpendicular. So we know this because we already found it over here, right? And we know that because how? We found the component of F, or a force component of F, in the direction of dE. So to get that component as a vector form, we just multiply the component, or the magnitude of that component, which is 394, by the unit vector along dE, which we already know over here, right? Which essentially means F dE is given by negative 334.25 times J. F is this entire vector, which I'm not going to rewrite. And F perpendicular is F minus F dE. When you do that, what you would get is negative 445.67 I plus 222.83 K newtons. So that's basically the vector that's perpendicular to the component of F parallel, or to the component of F along the line dE. And to find the magnitude of that vector, what you would do is just find the square root of sum of squares. So 445.67 squared plus 222.83 squared. And that will give you that this is something around 498 newtons. So that is how you solve these kinds of problems. So now let me move on to another problem that is similar in a sense. And this is problem number P115 or 2115 in your textbook. Now what this problem wants you to do is to find the component of the force F1 along the cable AC. There's also another force F2 that's given in the problem, which is not used in this problem. This figure is shared by two problems. So our only concern here is the force F1. So again, remember this is a 3D problem, so don't try to visualize it too much. Just find the coordinates and in turn the unit vectors that you want and solve the problem by trusting the math, right? So the coordinates that are important to us in this problem are the coordinates of A, B, and C. So I'll leave it up to you how to figure out the coordinates by yourself. And if you do that, what you essentially get for C is that the coordinates of C are negative 2, 3, and 4. For B, what you get is 0, 3, and 0. And for A, what you get is 2, negative 3, and 3. So the first step, obviously, is to denote F as a Cartesian vector, or F1 as a Cartesian vector, which is nothing but the magnitude 70 multiplied by the unit vector in the direction of A, B. So to find the unit vector in the direction of AB, what you do is find the position vector AB and divide it by its magnitude. And the position vector AB is 0 minus 2 is minus 2i, plus 3 minus minus 3 is 6j, plus 6j, plus 0 minus 3 is minus 3k. That divided by square root of 4, I'm just squaring 2 here. Square of 6 is 36, and square of 3 is 9. And what you get is that the unit vector in the direction of AB is nothing but negative 2 over 7i plus 6 over 7j minus 3 over 7k. Now, to find the Cartesian vector f1, what we do is just multiply 70 it's newtons by the unit vector AB. And when you do that, you would get negative 20i plus 60j minus 30k newtons. So what you have now is the direction, or the Cartesian vector, or the force F1 in the Cartesian vector format. Now to find its component along the line or the cable AC, we have to find the unit vector AC. So the unit vector AC is equal to the position vector AC divided by the magnitude of the position vector AC, which is negative 2 minus 2 is negative 4i plus 3 minus minus 3 is 6j plus 4 minus 3 is 1k divided by square root of 16 plus 36 plus 1 is equal to negative 4 or square root of 53i plus 6 or square root of 53j plus k over square root of 53. And once you have that, to find the component of F1 along AC, you just have to find the projection. And to find the projection, we just find the dot product of F1 with UAC, which is negative 20 times negative 4 over square root of 53i plus 60 times 6 over square root of 53j plus negative 30 times 1 over square root of 53k, which is negative 20 times negative 4 over square root of 53 plus 60 times 6 over square root of 53 plus negative 30 times 1 over square root of 53. And when you do the math, what you get is that the force component of F1 along, or the magnitude of F1 along UAC, or along the line cable AC, is 56.3 newtons. So with that, we come to the end of this video. We did 2 problems on 3-dimensional vectors. I hope that was helpful. Thank you.